Okay, the tests are done, and why is it not going away? Okay. And hand those back to you. Okay. So then I have your sheet. With your initial thumbnail, and are you okay? Okay. Is your initial A and K? Is that you? I do not have. Do not have a sheet? Okay. That's C, or is that C? Anyone else want their sheet cut? Matthew Montier.
Oh, yeah.
So the test worked out pretty well for most people. I didn't actually make solutions yet, but I took photos of few people's tests, so you can see them. I will post these later. Does anybody want to go over anything in particular on the test? Yeah, on the test. Pardon me?
Marking 3 points for like a side note.
For a side note. Yeah, if you're doing something and you think it's wrong later on, just scratch it out. Because when I see like really crazy stuff, I want to like mark that off. Well, I just decided to do it this time just because the test was actually, it was actually a fairly straightforward test. And so I wanted to see how clear you were. So when I'm looking, when I'm looking at your work, and especially if you didn't like box like what was the right answer, if you just had a bunch of random stuff on there and then the right answer embedded in there somewhere, it's not up to me to find, or determine which one's the right answer. When I see some crazy stuff there, I want to just mark it off because it looks really bad. So I did see that you had the right answer, which was good. So I marked off just a few points for people. Some people did things like, they computed a force, which was like 3 meters times g. I'm like, what? So I scratch it off and mark off points. You can't do that, right? If you're going to be, you've done this. You know how forces work. It's not meters times g, right? That's not a force. So you should train yourself to kind of think correctly and look for those errors, right? Later. Yeah, sure. So we can go over the second one. No, well, the last one I think is the most important. I was going to talk about, but I'm happy to cover anything. If there's anything on these that anybody had any questions about, let me know. And shoot, can I turn this? I don't know if I can. So turn your head sideways. The second one. What about the second one? Actually, should I download it? I could just download it. Probably be better. Is there a rotate button? Even better. Perfect. It said rotate was Control R, but let's see. Try that again. Oh, Shift R. Okay. So what are you doing on this one? So F1, right? That's a projection angle problem, right? So you got to figure out what's that F prime, which is the base of that vertical triangle, right? That's 450 times the cosine of 45, right? Now you take that, and to find the x component, I mean, I could still download it so we can mark it up if you want. Does anybody want to see me mark it up? The x component, which is I wish I had time to actually get this together. So let me try downloading. Or even better, I could do a snipping tool. I think that would be easier. And that. Oh, by the way, you know this? You heard about the STEM tutoring, right? So this is the schedule, and we're going to start on Wednesday. And if you want to know what subjects are being covered, just look at the list down here of those tutors, and then what subjects that they actually know. We hopefully will be expanding it, but that's kind of how we're going to start. Yeah, after 5. So the challenge about tutoring is now we have to have supervisors, faculty supervisors, and there is actually somebody volunteered to go like 6 to 8 or something like that. So we might have an evening session later, but we got to figure out the details on that. So snipping tool. And how do I make this thing bigger? All right. All these amazing tools, and they just don't do what you want them to do. Okay. Let's do fine. Sideways, open with. Paint. Trusty paint. Okay, now I can mark this up. As I was saying, the base of the triangle is that, and that has a length of 450 times the cosine of 45. Okay, and then what you do is you take, and that distance then is the hypotenuse of the flat triangle that's horizontal, right? And you're going to use that 450 cosine of 45, right? And you're going to use that as the hypotenuse of another triangle. So to get the x component, this is going to be this times sine of 30. And it's negative. So that's why the fx is that. Fy is that. Was there a particular part, Isaac, that you wanted to go over on this one?
Not sure if you go find x or find y.
If you want to bring it up here, I'll explain what my writing meant.
It looks like I did that the first half.
Yeah, you got the first half right. You got F1 right?
Yeah.
Okay. And then for F2, no, find gamma. You didn't find gamma. So remember, gamma is when you have the other angle or the other vector. This is a direction angle problem, right? And for direction angles, you need alpha, beta, and gamma, right? What's gamma? Sorry? Angle to the z-axis, right? Gamma is this angle here. It's a little hard to see on this vector, but gamma would be the angle from the z-axis to the vector, right? And you have to find that in order to get this thing written properly. Right? Remember, we did that. So, so to find gamma, we were given alpha and beta. Some people said gamma is just 180 minus alpha minus beta. That's not right. No, that's not right. No, good. Glad you didn't write that. Cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. You solve that for gamma. That's how you find gamma. And there's two possible values for gamma. It could either be 60 or 120 degrees. And in this case, since the arrow is clearly below the origin, is pointing below the xy plane, gamma has to be 120 degrees so that the cosine is negative. Then once you find gamma, it's just plugging that in to the third equation, 600 cosine of 120. This is gamma right there. This is beta, and this is alpha. Question?
I'm not sure each question.
Each question was like 30, 30, 40, something like that. Basically, it all adds up to 100, and I'm just sort of using some. It's not. I know some people like, well, I mean, it's kind of like what I'm looking for is the kind of error that you're making. If it's a serious conceptual error, or if you just like forgot to do a big part of it, like gamma is a pretty big chunk of points. Yeah, yeah. If it's a sign error, it could be 2 or 3 points depending on, Yeah, because there's only 3 questions. Yeah. Yeah, there's only 3 questions. So, yeah. Yeah, and any other questions on that problem? Then the last one had an easy way of doing it. I won't even probably download this one. You just rotate it. Wait, how do we rotate again? Where was that? It's not under more tools. What was that rotating thing? All right, shift arm, try that. Thank you. Okay, so this one, normally, I mean, I've given this kind of test before, and this third problem involves you actually have to use the dot product to find the answer. And a lot of people just run aground there because they haven't figured that out clearly enough to be able to do that on a test. And this one, the problem is in a section on dot product, it's asking you for the projection of the force along the boom. But if you're clever enough and you recognize this is a 3, 4, 5 triangle, you don't actually have to do the dot product to find the answer. You could just realize a 3, 4, 5 triangle means then that that theta is just 53.13 degrees. And so the parallel component part that's going along AO is the projection of the 80 Newton onto the XY plane with a 53-degree angle there to the XY plane. So the cosine of that is 48 times 80 is 48 Newtons. So I accepted that, and that was an easy out for people who could see that. What I was hoping some people would do is actually the way that these are the more general way, which can work even when you can't see that there's a 3, 4, 5 triangle, which is in general you can't. So, and that way you have to use the dot product, right? So for the dot product solution, we have Jose's. Jose got it almost right, and actually a lot of people like started using the dot product and then they sort of worked their way to figuring out what theta was just by like the Pythagorean theorem or something, and then they just they bailed at that point. They didn't actually follow the dot product all the way through. And Jose was one who actually did it all the way, but he forgot a little bit. He made a small error, and I can show you what that is real fast. And, can I draw this thing? Oh, that's even better. I can blow it up. And draw on it, then I'm happy. That's what I draw on. Size. There we go. Okay. So now I want to, no, I don't like this after all. So it downloaded it, but is that it? It's not showing up here. Okay. So for this problem, the answer is, so when in general, right, this is the kind of thing, and I'm gearing up for putting like some kind of a multiple choice final together and stuff. I'm really want you guys to get these things down because this is actually really important stuff. And multiple choice final will give me the opportunity to kind of ask a lot of short questions where you have to kind of remember these things, right? The dot product is your friend in these kind of problems. You're asked to find the projection of this force, okay, that is along the OA axis right there, right? That's what you're asked to find in this problem. And if it was a really arbitrary situation, like sometimes there's like pipes going different directions and you've got these axes with weird angles, you really can't tell what these angles are. So your only recourse, but you can, with a position vector, you can, and this is actually, is nice because these are set up with position vectors, right? You know that this is 80 newtons, so you got to make a position vector to find the force, so you find RAB, right? RAB, which is this position vector, right? And you find UAB, which is a unit vector along that direction. You find RAO, which is this position vector, and you find the UAO, right? And the formula for the dot product says that F parallel, and here's where Jose kind of worked it out here. The F parallel, or FOA, is going to equal the force vector dotted with, that's the dot, with not ROA, but UOA. Okay, right? Because remember the definition of the dot product is, FOA dotted with UOA is, you should remember this. This should have been on your formula sheet, right? It's what? And this is F parallel to OA is FOA dotted with UOA, which is the magnitude of F, sorry, it's not FOA, it's FAB. The magnitude of FAB, which is the force going up that cable, times the magnitude of UOA. What's the magnitude of UOA? What's the magnitude of UOA? No, what's the magnitude of UOA? What's the magnitude of UOA? What does U stand for? What does U stand for? Unit vector. What's the magnitude of unit vector? This is an easy answer. What's the magnitude of a unit vector? It's 1, right? This is why you're going to have more multiple choice questions, maybe as soon as test 2. Because these are really basic concepts. You should not be able to get a good grade in statics if you don't know the magnitude of a unit vector is 1. Right? You shouldn't. So you need to catch yourself on those things. And multiple choice questions are going to get you. And that's going to help you. And you're not going to like it, but it does help you. And I will, I've actually grabbed, all of the multiple choice questions from all of our lectures. I had somebody grab them all out. And so I have a big quiz bank of these things. And I'll post those so you can read them and think about what the answer's supposed to be. They're good questions. Yeah. Okay. So what does the dot product say? The dot product says the dot product of two vectors is the product of the magnitudes. What's the magnitude of UOA? It's 1, right? So times 1 times the cosine of theta. What's theta? The angle between those two vectors, right? The dot product between any two vectors is the product of the magnitudes times the cosine of the angle between them. Really, really fundamental, important stuff to know. And we already know FAB in Cartesian form, which is what Jose did. Right here, you got FAB. So you got UAB there. You got ROA, which would have allowed him to calculate UOA. The magnitude of ROA is 3, so just got to divide that by 3 to get UOA. And then here is his FAB, which is 80 times UAB times that, right, which gives you the Cartesian form of the force vector. And then you have the parallel component, which is dotting that with UOA, not ROA. In other words, if you just divide it by 3, you'd get the right answer. So he was very close. Correct answer being, what was it, 48 or something? 48. 48. Good. And actually, he had the right answer. Oh, he did it the easy way, too, and then he scratched it out. He took a gamble that the other way was right. And that's, I want you to decide. If you come up with 2 ways of finding the answer, you have to tell me which one you think is right. Yeah.
So for the, not the easy method, you chose it first. The dot product.
Yep. Yep.
Theta is still going to be the tangent inverse of 4/3.
It's the same theta. It is the the arctangent of 4/3 is theta. Sorry. It's the angle between the two vectors. The angle between, it's this angle right here. Or, I mean, it could be defined, depending on how you define OA. If you define it as AO, like pointing towards the origin, it's that. If you define it as going that way, it's this angle right here. It just gives you some sign issues, yeah. So I will publish these so you can kind of look at them more closely. But that's kind of what I was looking for in general. But like I said, if you could see, I figured, well, if you can see if you have the clarity to kind of see the easy way, I'll give you guys full credit for that. But that made it a really easy test, because that means you didn't have to do the position factor, you didn't have to do the unit vector, you didn't have to do the dot product. You have to know all those things. You can just see that, right? You got away with it. So that's why it was kind of an easier test than normal. And that's why I said, well, I'm going to start looking at crazy stuff and start marking people off for crazy stuff if they didn't actually eliminate it.
So does that mean the next test you won't grade as harshly?
As next test, I won't grade as harshly. The next test, you can expect it to be harder, though. Yeah.
You said like this time.
Do you think that's harsh? I mean, 3 points is not a huge deal when you do something crazy. I don't think. Yeah. As long as you don't make a habit of it. But I want you to catch those things, right? Because you got to, like if you're presenting your work, this is my work as an engineer. And if if you're doing some really crazy unit stuff that doesn't make any sense, I need to point that out for that, so you don't actually. And what was funny, you could do that and still get the right answer, right? And that's worrisome in the sense that, engineers, you got to get the right answer using the correct means, right? Because sometimes you can get the right answer by lucky guess. You can get the right answer by just 2 errors canceling out. That happens a lot too. You really need to, I still have to mark you off for that, even if you get the right answer, right? Yeah, there are these things that, you're like, oh no, I got the right answer. Why did I lose points? I'm showing you, errors in thinking and stuff. That's what I'm doing. Yeah. Okay, any more questions about the test?
I noticed that I tended to, when I was summing up the components,
Yeah.
I tended to put in terms of X and Y, but it seems like I kind of confused them a little bit more, whereas like I looked at another test and there was other components that put into like F1, F2, F3, instead of like F of X, 1, 2, 3, F of Y, 1, 2, 3.
Yeah, if you want to show me something, I'm having a hard time understanding what that question is about.
I was wondering if like one way is more beneficial.
If you could show me, I could give you more insight. I'm not clear what you're asking, or I'm not clear what the notation issues are that you're saying. Yeah. Yeah. So that's the first test. There's going to be 3 more tests, and yeah, they're going to get more challenging, as you know. So we haven't. I haven't graded assignment 3 yet. Unfortunately, I just had a really busy weekend. But assignment 3, 4. I think there's actually 3, 4, 5. I think those 3 are going to be on the next test, or maybe 4. Maybe 3, 4, 5, 6 are going to be on the next test. So yeah, now that we're going, I want to stay on top of these things. So I was going to ask if anybody wanted to ask a question about homework 3, or also homework 4. Homework 4, I'm sure, is fresh in your mind, but we didn't actually go over homework 3 yet. I have solutions if anybody wanted to do that, or I could just kind of go over a solution approach to that. And then basically the plan for today was to, after taking any questions, I will give you an overview of this week's topics, right? And then I've already posted the lecture videos for those. You've got those sheets, so I expect you to kind of watch the videos, and if you could do them, if you could watch them both by tonight, I don't know if that's feasible. Again, you can kind of, they're really not very long, especially if you're playing at 1.5 tons or something, right? And go through those problems and kind of get the basic ideas down that we're doing. We're going to come back, and we'll have 3 days to do problem solving then in class. So you'll get a lot done on the homework this week. There's a quiz also, I think, on Thursday. It'll be online.
Sunday or Friday?
Yeah, I think it's by Saturday. I think it's by Saturday or Sunday. I think it's Sunday. Yeah, due by Sunday. So homework 3. Let me see. These are the solutions to homework. That's the solutions to homework 3. Does that look familiar? There was that problem, this problem, these guys. Remember that one? Any questions on any of these guys? Remember that one? Maximum tension problem. That crazy one. The last one? Sure. And as far as I don't mind actually if you are trying stuff out on the test and you're not sure about stuff, and then at the end though you should look at your work, and if there's parts that you don't want me to like like if like you were drifting off or something, you could just X those, and they don't pertain to your main solution. You can X those out, and I won't make you lose any points for doing that. Just you got to realize someone's going to be reading this thing, and they're going to be confused if you don't. If you have confusing stuff on there. So the question was on the last problem, which is a really kind of a really cool problem. Conceptually, what's happening with this problem is this central mass, which is 3 kilograms, is being perfectly balanced by these 3 side masses hanging off in a sort of a tetrahedron sort of shape. And there's a geometry thing involved there, so you can kind of see that there's a tetrahedron, and you're trying to find what's the balancing point. How far is that thing going to sag before all those 3 forces balance? And you can kind of do a little thought experiment by thinking about what's going on with these forces, and you can kind of see, I think, for yourself if you draw the free body diagram like so. You've got TA, TB, TC. Now the magnitude of TA, TB, TC is what? Yeah, the weight of these guys, the weight is 2 kilograms times G, right? So, a little less than 20. So that's these guys, right? So the magnitude of those things, but what you don't know is the angle to the vertical, like this angle, they're calling it gamma, which sort of makes sense. The angle to the vertical for each one of those things, that's the important angle, because that's going to determine how much of TC is actually lifting up the box. And you can see if if the cables were really long so that the angle gamma was 0, you would actually have 3 times those TCs to lift up that central mass, right? But the central mass is not 3 times the mass of the ones on the outside. It's only 1.5 times those masses, right? Or it's this is 3 times 9.8. You potentially could have 2, 4, 6 times 9.8 if they were all vertical going up, right? Which is twice as much as you need. So there's going to be a point where it balances, where if it goes too if S gets too small, those weights aren't going to be heavy enough to pull it further. If S gets too long, those weights are going to be too light. So so we're trying to find what is the S for balance, for equilibrium. And you propose that there's a gamma here. And if you just add the Z components together, which is going to be you've got 3 masses times the weight, or times the mass, 3 of these times the mass times G, that's the total weight times the cosine of gamma, is the total vertical force. And it's, and then the downward force is just this guy times 9.81. So that's the weight here, maybe the weight of the big guy. And then these are the 3 small guys, and they're scaled by cosine of gamma. That is equals 0. Now you can solve that pretty easily and find that gamma is going to be 60 degrees. And it might not be too hard to get to that point, but then the question is, you've got to turn that into a distance, a position distance. So you've got to go from these forces to some kind of distance, and that's where the geometry is involved. They make it look so easy here. And you can sort of see it from the picture. It's a pretty nicely drawn picture. It's got a lot of information in there, but you can see that this is an equilateral triangle with 1 meter on each side, right? And you can then say, well, you can bisect those, each of those angles where the center point is, and then you've got basically, 0.5 meters on a right triangle, and this becomes like a 1, 2, √3 triangle or whatever, right? So this is but this is 1, this is 1/2, and then this is going to be, this distance here is going to be √3/2. And what we're trying to find is if we know that this angle here is, let's do a vertical slice here, is 60 degrees. If we happen to know what this distance d is, then we could figure out, using our trig, what d is. And d is the distance between the peak of the triangle and the center. And you know that the side is 1 meter. So there's a few ways. So if you kind of look at this thing, this is 1 meter, and this distance here is these are 30-degree angles, right? So basically we're saying, 0.5 over the 30 degrees is 0.5 over the cosine of 30 degrees. Actually, I'm sorry, this is d here. That's d, and this distance here is 0.5. 0.5 d and 30 degrees. I don't know, hopefully this is helping. It's kind of a messy to write down at the bottom of that screen. Oh, there it is. Right, so this is 1, or this is 1 here. You divide that in half, that means this is 0.5. And then this angle here is 30 degrees. And you're trying to find that distance, d there. And that gives you 0.577 meters. That's the distance from the side to the center of the, actually, no, they're actually finding, what are they finding there? They're finding this distance d here. Yeah, so this distance is d, the hypotenuse of that triangle. Okay, that's d. And that's 30 degrees, and this is 0.5. And so d times the cosine of 30 is 0.5, so you can solve for d that way. And then s is another trig thing. If you know this is 0.577, and you know that this is 60 degrees, then you can find s using the tangent, because d over s is going to be the tangent of 60 degrees. So you can use that and solve for s being 0.333 meters, or 333 millimeters. It gets tangled up in the geometry there. That's why it's sort of a really interesting problem, because you're going from, this force system, equation of equilibrium, to then some weird geometric problem. Yeah, like I said, I didn't expect everyone to do that, but I like to put these on there because, this is engineering. One thing that people report back when, after they transfer, people that often got like perfect scores on all the tests, that never happens after you transfer, because they put problems like these on tests sometimes, really challenging problems. And the reason they do that is because, like if you go to Berkeley or, UC schools in general are kind of like that. They consider, if someone gets 100 on a test, they consider that person really hasn't been challenged yet. And so they want to make sure that nobody gets 100 on the tests. So they'll actually add really, really hard questions on the test to see, to really make sure people get the challenge, right? So that's gonna come at you. So I think it's important to put these in here so you get exposed to them, just like, other people are going to get at the universities. And it's, you're gonna be challenged. And, if you don't get them all, it's not the end of the world. But you're going to have an opportunity to really, expand your problem-solving ability. And I want to make sure you get that opportunity in the test, in this class too. I would never put this on one of our tests, though. Other teachers might, though. I don't know. Should I? It'd be really painful. I'd have to grade it. That's the problem. Kelly? Okay. Are there any more questions on homework 3 before we go to homework 4? Recall anything? Okay. Then let's look at homework 4. This one there? So there's one more?
Yeah.
There's the last one. You want to go to the second to last one? 418? That one. Yeah, oh, that's a fun one. So you've got a gate, and 2 kids are playing around, and they're pushing each other, pushing the gate, and or actually, I guess they're pranking each other, right? I think the guy at A is sort of maybe pranking the guy at B. I don't know. So A is like hiding and trying to exert a force to keep B from opening up the gate, right? So do you want to just go over it, the solution? Or do you have a particular question about it? Or? Oh, you have an answer?
No, I don't have to. I don't have to.
You haven't figured it out yet? Okay. Were you here on? Were you here last week? You were here for one of those days, right? Or were you here for? You were here on Thursday, right? You were here for both. Okay, good. Yeah, it takes a while to kind of process all these things. So, did it save you? Was it better, by the way, to do it that way, to have the in-class problem solving as opposed to kind of having lectures? What do you think?
I don't know. I feel like it was better before, but still getting used to it.
You kind of liked it better before?
Yeah, a little bit.
Okay. Were you able to watch the lectures before the class?
Personally, yeah.
Okay. That would be really important, right? Because if you can do that, then it's pretty similar to what it was before. You just have more time in the classroom. Isaac?
For me, the worst thing is being on a problem. I'm getting stuck, and I'm like using all the resources I have, and I'm still in it.
Uh-huh.
So, like, people in class,
Yeah, and one strategy might be instead of like when you're in class. So the thing was getting stuck in a problem is a real pain when you're working by yourself, which is what most people do, right? Now the stem cell is starting up, and so if it works conveniently, and you can see when there are some people that are in statics in there, LRAs is going to be in there, and Mansour is going to be in there on Fridays. You can drop in there and get a lot of work done. Again, in like a cohort, right? Which is how you're going to have to. This is how you're going to have to solve your homework problems after you transfer. You're going to have to be in a cohort. So I'm trying to get people to move away from having to work all by themselves, at night to solve these things. Because when you get stuck, there is no recourse. There's nothing you can do. Really, I mean, when you're really stuck. I mean, you can go for a walk, think about it. In fact, you got to learn how to kind of get over that yourself eventually. But typically, the problems are so hard that it just may not happen. But being in a group makes it a lot easier. So we do a little bit of that here. And you might think of maybe this week when we, after we do the in-class problems, we'll do those all the way through. But maybe the other problems, you actually just work out the plan. So you actually hash out the problem-solving plan that you're going to do. And then you could go through and do the plan for all of them more quickly. So then you go home and you just got to flesh out the plan on your own. I mean, you might try we might try that this week, maybe on Thursday. But anyway, looking at this problem, so what is the issue here, right? You've got to find the balancing of the moments that each one's providing around the hinge of that gate. The hinge of the gate is where? It's at C, right? And So, so we need to know that, and of course, if you break the forces up into the y and the x components, you're going to have something that looks like this. Now, are the x components going to matter in terms of balancing out the moments? Which component really matters? The y components matter, because the x components are actually pointing right at the hinge, and so they're not going to provide a moment either way. Yeah. So it's really FAY and FBY that matters, right? And the sum of the moments at C has to be 0. And if I was going to write those out, how would I write out the sum of the moments at C with those two forces, FAY and FBY? Yeah, I got 6 times FBY, which is going plus or minus. Yeah, it's trying to make it go that way, and we're going to call that the plus direction, right? And I've got something times FAY. What's the moment arm for FAY? 9. So minus 9 FAY. Well, that has to equal 0. Okay, and doing that, you can, since you know that FB is 30 pounds, you can find out what FBY is. And then you can find out what FAY is, and you can figure out what FA is from the angles. Right. Yeah, that's the plan, right? Once you see the plan, then it's like, oh yeah, that's pretty easy. So if you just did that on our problem session days, that might be sufficient to get you through the homework a lot faster. Hit them all, get a plan of attack for them all. Yeah, yep. Then all I gotta do is work it out. Yeah, so we could try that this week. Well, we are rapidly running out of time here, and I wanted to just talk briefly about the topics for today. And this week we're going to be doing moments in 3 dimensions, and also finding a moment along an axis. And I kind of thought this might be, rather than kind of flipping through the slides, which you're going to get in the lecture, we can maybe just look at the problem handouts that I just gave to you guys, which is what what you're going to be solving here. Now, we start kind of, again, reviewing moments in 2 dimensions, which are, what we did in homework 4. Just to kind of ground you, right? A moment in 2 dimensions is just the force times the distance. The distance is the perpendicular distance from the line of action of the force to the axis that you're finding the moment about, right? And in terms of the moment, it looks like a scalar, but there is a sign involved. And we use these curved arrows to indicate like what our sense is for that moment, right? And actually, I was just thinking about this on assignment 4. What engineers often do when you're doing a 2-dimensional moment is they'll do something like this on their equations. And that indicates what they're considering as a positive moment direction in 2 dimensions. Counterclockwise is positive. And that allows me, and if you do that, that allows me to see, and you to see if that's, is that correct? Is the moment of FBY going counterclockwise? Yeah. Okay, but that's just a 2-dimensional situation, because in general, moments are actually vectors. And in 3 dimensions, you've got to do a cross product. And so the actual moment definition is the cross product of a position vector to the axis that you're doing it on, or to the point. Actually, this is a moment about a point, point O, and it's crossed with the force vector F. And the cross product is defined as the product of the magnitudes times the sine of the angle between them, isn't it? And so it's a perpendicular kind of thing. When the angle's 90 degrees, that's when you get the biggest cross product, when you get the smallest dot product. So you can see what's involved here. You've got to find a position vector, ROB, and an ROB is the vector. It's a position vector connecting point O to the force line. However, you have this flexibility because you could also use OC. ROB could just be any position vector connecting the point of the moment to the line of action of the force. And that's what you're going to be looking at today. You can see it gets a little more, quite a bit more complicated. This is showing you how to find the moment of F about O. And in this example, you're going to be using like OC as your position vector. ROC crossed with F is going to give you the same answer as ROB crossed with F. And that's what you're going to actually work out. And then another example, again, finding ROA cross F. You're going to be doing these cross products, right? And then in the second one, you're going to find the moment about the OA axis. And I might have actually given you the wrong handout for the second one, which is unfortunate. I did. So actually, if you want to just hang out for a second, I will launch the correct one to the printer. That one I gave you, I think it's from last week. Because the interesting thing, again, going to the moment about an axis now is where you have, maybe you want to find the moment about the OA axis. You want to know how much is that force contributing to like a rotation trying to get that pipe to spin about its axis, OA. And that involves what's called the triple product. You've got to do a dot product with the axis vector at the very end of the calculation. So again, and I think you've got this in 20C, right? The triple product, they call it, right? We call it the triple scalar product or the triple product. You get that. You can do that. So it's actually kind of nice. It's an application of the triple product. You're going to see how that actually works. But let me, you can just chill for a second. That is the plan. And this is, yes. I got the wrong one. There are 5 of you. That's what I'm printing. Perfect. Okay, so tomorrow we're going to dive in on these.